going?
You said the quiz is going to be at the end of.
Yeah, we did.
Oh, they are.
Yep.
Okay.
Any other questions at all? Let's pardon me. Let's do one more example with applications of quadratic functions, and I'll leave that last one for practice, and then we'll get into some new stuff before we take the quiz at the end of the hour. So let's look at this first one here where it says we've got a rectangle. They tell you that the length of it is 3 more than twice the width. And then it asks you what's the minimum area that the rectangle can have. So in a problem like this, when it's asking you a minimum or a maximum of something, the first thing that I would do is write down a formula that you know that gives you the value that you're looking for. So in this case, we're interested in area of a rectangle. How do you calculate the area of a rectangle? Length times width, right? So I know that the area is the length of the rectangle times the width of the rectangle, right? The problem with this particular function is that it has 2 variables in it, right? I don't know what the length is, and I don't know what the width is, right? And this is pretty typical in problems that you come up across that they just tell you find the maximum value but don't give you an explicit function. Usually that value that you're looking for is going to be inside of a function that has 2 variables in it. So there must be some other piece of information in the problem that tells you how to get rid of one of the variables in terms of the other. What information are you given that relates the 2 variables in this one? What other information are you given in this problem? Yeah, the length is 3 more than twice the width, right? So in this case, I know that the length is equal to what in terms of the width? Twice the width we would represent as 2w, and then 3 more, whoops, 3, yeah, good, plus 3, right? So that's the other piece of information that we have. Once we have this information, we can plug this in for L, and we get a function that's just in terms of W. And now it looks like things that we've done before, right? Now we have an explicit function that's in terms of 1 variable. And we've done problems where we find maxes and mins of this type of problem, right? Okay. What do you think we should do first before we try to do anything else, just the way this function's written? What do you think we should do with this W? I would distribute it. Yeah, that's what I would do. Because now we see that we have a quadratic function. And by the way, anything that you're going to be asked for in this particular section where it asks for a maximum or a minimum value, it's going to be of a quadratic function. So whenever you find this function, it should be a quadratic one. Okay. How do I know that it's going to be a minimum that comes out of this versus a maximum? What tells you that we're going to get a minimum value versus a maximum value? Yeah, the positive on the W squared, right? On that squared term, the value is, the coefficient there is positive, so that I know the parabola goes this way, and so the vertex is at the bottom. So we want to find the vertex of this particular parabola. Like I said, in your application problems, I'm not going to expect you to go through completing the square. Okay, if I want you to do completing the square, I will literally say, use completing the square. Okay, that will never be in an application problem for you. Okay, I want you to use the shortcut. What is the shortcut? How do we find the x coordinate of the vertex using our shortcut? That's then negative b over 2a piece, right? So in this case, if I want the x coordinate, or the w coordinate, if you will, it's negative b over 2a. What's the b value? 3. And that's interesting. Why is it negative? The a is 2. Interesting. I did something not quite correct here. Because this is 2 times 2. I'm getting a negative 3/4, aren't I? What's wrong with that? Yeah, the width of the rectangle can't be negative, right? That's an issue. The problem should, I typed this out of somewhere else. The problem probably should say 3 less than twice the width, so that I'd have a minus 3 here. Which would make a lot more sense, right? But in any event, it doesn't matter that we've got some answer that doesn't make sense in the context of the problem. This is how you find the x-coordinate of the minimum, right? Regardless of how it is. Okay. Like I said, this particular problem, the context has a little bit of it. There's a little bit of a context issue there as far as having a width that's negative 3/4 in there. So like I said, it probably should say 3 less than twice the width, which would make that value positive. So just so that it makes sense in context, let's assume that it's a positive 3/4 rather than a negative 3/4. Regardless of what the x-coordinate is, the problem is asking for the minimum area, right? Is this the minimum area? Regardless of what the context is this the minimum area? No, it's a width value, right? So if you wanted to find the area, what would you do with it? Plug it into the function, exactly right. To find the minimum value, we would plug it in here, right? So the minimum value, and again, I'm ignoring context because, like I said, this problem's already defective because negative 3/4 doesn't make any sense. Okay. The minimum value would be plug in negative 3/4 into the function, right? And then we would have 2 times negative 3/4 squared plus 3 times negative 3/4. Again, look, this is context independent. What do you get? You get 9/8 when you simplify the first part, and that would be minus 18/8. So it looks like you get a negative 9/8 when you're done. I did the arithmetic correctly. Calculators for. Again, ignoring context. Is the process okay? So again, like I mentioned, if you've got a problem that's asking you for a minimum something, it's not giving you an explicit, or a maximum something, and it's not giving you an explicit value, you want to write the function down first. So let's look at this. I'm not going to go through the whole problem. I'll leave the finishing off to you for practice. But let's say we've got this problem where you're going to have 100 yards of fencing. The rancher wants to maximize total area, right? Agreed? Okay. So again, we're trying to maximize an area. We know an area is a length times a width idea, right? Okay. So, but in this case, we might want to label the pieces individually rather than just saying a length times a width. So maybe we want to call these 2 dimensions x and these 3 dimensions y. If I do a length times a width or a base times the height, my height here is just the y, but what's my base? 2x, right? So what would the area be? 2x times y. Good. That's exactly right. And the reason why I broke this into pieces is why. Why did I break it into pieces? Well, the information that we're given is, how many feet of fencing? 100, right? How much fencing do you see if I've got these labeled as x's and y's in this fashion? How many x's do you see for fencing? Well, I got 2 up here and 2 down there. So how many total x's do we see? 4. How many y's do you see? 3. So what equation might you set up now? I need total fencing is 100. And you just told me you see 4 x's and 3 y's. So what equation might you see? total fencing, and you have 4 X's and 3 Y. How do you total something? Yeah, go ahead.
4x plus 3y.
And what should that equal? 100. Good. Exactly. I've got a total fencing needs to be 100. You total by adding things up, right? You're looking at basically a perimeter idea. You just got a side in the middle, right? So the other equation that you would have would be 4x plus 3y equals 100. Again, notice, like I said before in the previous problem, the area here is a function of 2 variables. I need to get rid of one of them before I even try to attempt the problem, right? There has to be some other information in the problem that tells you how to write one of the variables in terms of the other. That's in terms of the perimeter here. So what do you think we should do with this equation now? I'm trying to get rid of one of the variables in the area function. So what do you think I should do with this equation? Yeah, isolate either x or y. Solve for one of them. Doesn't matter which. I'll solve for x. Bless you. Only because the 4 evenly goes into the 100. Bless you. So my x is negative 3y plus 25. And then what do you think we do with that? Plug in for x into your area. And now attack the problem just like we did the previous one. So I'll leave that for you to finish. But that's the basic idea in doing these maximum and minimum problems. Like I said, a lot of times you'll get a function of 2 variables, an expression in terms of 2 variables that you're trying to find the maximum or the minimum of. So there has to be some information in the problem that tells you how to get rid of one of the variables. So set up an equation like we did here and solve for one variable in terms of the other. Again, I solved for x only because I could divide 100 by 4 evenly. So I got rid of one of the fractions. I could have solved for y as well. But now attack that problem, just function, just like we did the previous one. What questions do you have? Bless you. What a sneeze is going on. All right. Let's talk about some new stuff. All right. So we talked about quadratic functions in section 3.1. And we've talked about linear functions in a previous section. What was that? 2.5. Both of those are special examples of, or special cases of, what we refer to as polynomials. So our whole point of this particular chapter is to try to do, sorry, Logan, I do that every time. The whole point of this particular chapter is to try to do as much analyzing of polynomials as we possibly can. Okay? And eventually we'll get to a point where we just can't do anymore before we need calculus to do some more things. Okay? So that's the whole point of this section, or this chapter, I mean. In this section, we just want to introduce some behavior pieces of polynomials. And I'll talk about what I mean by that as we go through this the material here. All right. So just a refresh of what we mean by a polynomial. What we mean by a polynomial is that our function looks like the following. So I know it looks a little bit gross with all the letters and all the subscripts and all the superscripts. So let's talk about what each piece means. First, all of these subscripts just mean that they're attached to the x to that particular power. So the a sub n just means that's the coefficient on the x to the n term. The a sub n minus 1 just means that the coefficient of the n minus 1 piece, and so on down the line. We want all of these coefficients, this a1 out to an, are real numbers. And the n is a non-negative integer. So I know lots of words, but let's talk about what each of them mean. Real numbers again, those are the numbers that you're used to dealing with. They include the whole numbers, right? The no decimal parts, the fractions, and the things that aren't fractions, right? Like square root of 2 and pi and e and all of those things. Okay. So what we mean by real numbers, non-negative just means it could be 0, but it could be positive. Integer just means no fraction. Okay. So as far as a polynomial goes, when you see a variable, you can only raise that variable to a positive integer power. Okay, so polynomials don't have roots, they don't appear in denominators. Okay, they're very, very special types of functions. Okay. So we do polynomials, we do not divide by variables, you do not take square roots of variables, any of those types of things. Okay. Don't take absolute values of variables, right? All right, so let's talk about some important vocabulary that we need that's going to help us identify important pieces of the function going forward. So the first piece is we refer to as the degree of the polynomial. This degree is the highest power of x that appears in the polynomial. And it's literally the number. So the number, the degree is the number of that exponent. The coefficients, those are the numbers multiplied by the powers of x. So the way I have the function written there, the coefficients are the a0, a1, ... up to a sub n. The constant is that last term that I have written there. It's the number with no x next to it. Or if you like this better, think of it as an x to the 0 power multiplied next to it. Right? X to the 0 would be 1. So up here, where I wrote this a0 here on the end would be your constant term. That has an important quality for the graph of the function, and we'll talk about what we mean by that in a little bit. Leading coefficient, in this case, that's the number multiplied by x to the highest power. So again, like the constant, that number, what we wrote up at the top was the a0. In this case, when we're looking at the leading coefficient, that's the number that's being multiplied by the x to the n. Okay. The leading term means that you put the constant or the leading coefficient with that highest degree term or highest degree of x. So just to write it in the way we have it written up there, the leading term is that a sub n x to the n. It's the coefficient with the x to the power. And this is going to have importance to us here in a minute that talks about what happens as x gets really, really big. That's the piece we're going to look at. Okay. All right. So let's see if I can identify the different pieces here in this example. What's the degree? What's the degree of this polynomial? Yeah, it's the 4, right? It's the number that's the highest power that we see here is x to the 4th, so the degree is 4. Or we also would say this is a 4th degree polynomial. Okay, so the degree is 4. What are all of the coefficients here? What are the coefficients that you see? Yeah, -4, 2, 1, -1, and 6, right? So on the x to the 4th term, your coefficient is -4. On the x cubed term, the coefficient is 2. X squared, I probably should be putting colons rather than hyphens like that. X squared term is 1. It's a 1x squared. X term would be -1, and the constant term is 6. The constant counts as one of the coefficients because, again, you can think of that as being multiplied by x to the 0. So the constant still counts as one of the coefficients. In particular, the constant term is 6. You can see that from the coefficients. What's your leading coefficient? -4, good. And our leading term then is -4x to the 4th. Good. That's exactly right. Again, the two big things, the constant term and the leading term are going to tell us information about the graph in this section. Okay. So those are the two big things that we're going to have here. Any questions on finding those values out of that? All right. So what does the leading term tell us? And we'll finish this up on this page, and then we'll have your quiz. What is this is what we're referred to as the end behavior. What we're talking about with end behavior graphically is basically which ways do the ends point. What I mean by that is when you have x squared, both of your ends point up or down, right? When you've got x cubed, one goes up and one goes down, depending if it's been flipped upside down or not. X to the 4th, x to the 5th, x to the 6th, x to the 7th, right? And we know that the highest power term is the one that's going to take over when x gets really, really big. So when we analyze end behavior, that's exactly what we're going to look for. So let's write down what these symbols mean. When we write this x, right arrow, and infinity, so we say this is the way we read this is as x goes to infinity is how we read that. What we mean is that x gets really large in the positive direction. So what do you think the next symbol means in the second line there? Exactly right. This means it gets really large in the negative direction. All right. So that's what those symbols mean. And we're going to describe end behavior using those symbols. So by end behavior, we mean what happens to the outputs to f of x as x goes to infinity and as x goes to minus infinity. This is just basically math speak for how your tails are going to point. We're just going to write it with math symbols. Okay? So again, like if we have positive x squared or negative x squared, both ends are going to point the same direction, right? Both point up, one point down, depending on if you go positive x squared or negative x squared. When you have x cubed, one points up, one points down. X to the 4th, they both point the same direction. X to the 5th, one goes up, one goes down. So it's going to tell us if we have even or odd, it's going to tell us how it really works. Okay. So the term that's going to we look at is going to be that highest degree term or the leading term. That's the thing we're going to look at for in behavior. So what we'll talk about on Monday is we'll fill out this table to summarize what we mean by this. And we'll do some examples. And we'll also get into pardon me. Also get into talking about x-intercepts and y-intercepts and how we find those. I want to give you plenty of time for the quiz, which is why I'm knocking off early.